All right, so out of 12.7, look at these two questions. So 29 has the sum from 1 to infinity, log of n over n times x over 2 to the n. All right. And so you're supposed to find the radius and interval of convergence, and the radius of convergence and the interval of convergence for the given functions. So you could just start applying the ratio test, and I suppose that's fine. But let me point out real quickly, right? If we want something to be a power series, it's got to be something times x to the n, right? Or x minus 5 to the n, or something, not x over 2 to the n. And so it's fine to sort of do the power series, but and then just realize, right, I'm raising x to the n, that's the term I'm going to deal with. And so you can do it that way. I'm just going to do it explicitly, though, and break it up like that. Does that make sense?
Yeah.
So now I have something times x to the power. And now I'll apply my ratio test from there. So log of n plus 1, x to the n plus 1 over n plus 1, 2 to the n plus 1 times n to the n log n x to the n, right? And same kind of cancellations happen as always. The log and the polynomial never cancel out though, right? So those guys are going to just stick around for the rest of the problem. But the x and the 2 will cancel in the same way they always do. So we end up with, and I'll just write it like this. Right, there's my logs together, and then I have the polynomials. That'll be what? So let's just do this. Canceling these guys, right? And so what's left with the n and the n plus 1? It'll just be n over n plus 1. That makes sense?
Yeah.
And then finally just absolute value of x over 2. Okay? So what does n over n plus 1 approach? As n goes off to infinity? 1. What about log of n plus 1 over log of n? It's also 1, right? If you had to show it, you do L'Hopital's rule, but we've seen these enough. As long as it's the same sort of linear polynomial inside, that's going to go to 1 as well. So this whole thing goes to 1, 1, and so the entire limit goes to absolute x over 2. That make sense? So now you set whatever you come up with equal to 1, right? And solve for the whatever x was, x minus whatever, in this case x minus 0. You get 2, and so your radius of convergence is 2, right? And so what are your endpoints?
2.
Yeah, so 2 and negative 2, right?
Yeah.
So if we plug in 2, and we can just go back to the original. I'm just going to do it in our head, right? 2 goes in there, so you'll get just 1, right?
Yeah.
So 1 to the n, so you just get log n over n. And so does that converge or diverge? Diverges? I agree. Why?
Harmonic series.
Yeah, the harmonic series is 1 over n, right? So if we add a log in the top, we've gotten even bigger than 1 over n. And so I'll just say log of n over n is greater than 1 over n, right? Which is, so I'm just going to leave it like that, so okay. And as long as you notice something, just give me evidence that, yeah, I see it's bigger than the harmonic series, so it diverges. What about at negative 2? So what's the difference this time? I plug in negative 2.
The equation just becomes negative natural log n over n. It's just negative.
Not just negative, but negative
To the power.
negative 1 to the n, right?
Okay.
Right, you put in negative 2, the 2's cancel, and you get negative 1 still being raised to the n. Does that make sense?
Yeah.
Okay, so again, this guy diverged because it was bigger than the harmonic series, but right, log n over n does go to 0, right? And it will eventually decrease And so in the middle of one of these problems, you don't have to show all the details of the alternating series test, but you should realize it applies here. You got an alternating series whose terms go to 0. Again, you could come up with weird examples where that doesn't mean it's decreasing, but in this case, it eventually decreases. If you had to, you could take the derivative of log n over n, show it's negative. You don't have to do that here, but you should conclude that this guy converges. Alternating series test. Does that make sense? So again, you don't necessarily show all the work, but you should understand sort of the work behind it. Again, in the middle of the summer, this goes so fast that it's like, oh, we did this a long time ago. Well, it wasn't a long time ago, but we treat it as though it was a while back. All right, so what's that give us then? So the interval of convergence is, well, we went from -2 to 2, and then what brackets do we want here?
A closed for -2 and open for.
Right, closed because it converged at -2, open because it diverged there. Okay? All right, and then the other one was, what, 35? Start this one below there. Okay. So 35, we have the sum from 0 to infinity of 1 minus x to the 2n plus 1 over n factorial. So this one you could actually just do the ratio test and the problem's done pretty quickly. But let's just talk this one out a little bit more detail than you actually have to. So remember, right? We said here's this series. You get x to the n. So this one's centered around 0. Where is this one centered around? Around 1, and so this might be overkill, but there's going to be times where it'd be better to look at this guy like that. Does that make sense? Right, where because when we want to find that, if we wanted to find the sort of sum or the radius of convergence, we want to isolate the absolute value of x minus 1, which happens to be the same as the absolute value of 1 minus x, but I think it's worth at least noting in this one that that happened. And then let me also just say, so this breaks up like that. What's -1 to the 2n plus 1? So n 0, 1, 2, 3. So it's the same though.
Always -2.
It's always -1 because 2n plus 1 is always odd, right? So that's always just -1. So you could really just drop this off of there and just leave it as -1. Okay? Now, that being said, on this particular problem, you don't even have to worry about that. Let's just start from here, okay? And let's apply our ratio test. So you take the limit as n goes to infinity, absolute value 1 minus x to the, well, let's be careful here, what power? 2 times n plus 1 plus 1, right? And then all over n plus 1 factorial, and then times n factorial 1 minus x to the 2n plus 1, right? Factorials cancel just like always. And then let's just be careful with the power here. So what is this? I'm going to just write it out up here. 2n plus what?
3.
3. Does that make sense? 2 distributes through and you get that. So now we cancel the factorials. We're just left with n plus 1 in the bottom. And what about the 1 minus x's?
The bottom cancels.
All of this is gone, leaving us with how many up here?
2.
Yeah, there were 2n plus 3. We got rid of 2n plus 1. So there's 2 left over. Does that make sense?
Yeah.
So then it'll be, I would write it absolute still. Right. 1 minus x squared. So now, you have to be careful. If this turned out to be some limit, you do have to worry about that square, right? If this was the limit was 4, 1 over x, the absolute value of 1 minus x squared equals 4, then to find the radius of convergence, you actually have to take the square root, because you got to get the absolute value of 1 minus x, or x minus 1, not of it squared. In this case, it doesn't matter, because if x is fixed, 1 minus x is fixed, 1 minus x squared is fixed. So what is the limit over n plus 1? It's going to be 0, no matter what x is, right? And so you get a limit of 0, that's less than 1, and so what's that mean?
Converges.
Converges, and so our radius is
Infinity.
infinite, and then your interval, you can write out the interval goes from negative infinity to infinity, but once you say the radius is infinite, that should be enough.
Okay.
Does that make sense?
Yeah.
Okay, anything else out of 12.7 then?